All right, so empirical and molecular formula are a quantitative way two techniques to quantitatively decide or look at what a formula should be. So when we did naming in Unit 2, all we did were compounds that had two nonmetals for covalent, or maybe we did ionic with a polyatomic ion, but we didn't really talk a lot about where, for example, a polyatomic ion like chromate, where does that come from? CrO4 2 negative. How can compounds exist with that don't follow the crisscross rule in covalent where they're sharing? What happens if you have three nonmetals? So their compounds are not as simple as we have discussed. There is many very large molecules. Yesterday, some of you did a question with sucrose and you saw how many carbons and hydrogens and oxygens there were. Sucrose is called a macromolecule, a very, very large molecule. So we would like to quantitatively figure out the formula of compounds. So we're going to look at how to calculate the empirical formula. Then we'll look at how to recognize whether a formula you're given is empirical or not. And then we'll talk about what molecular means. So when you have an empirical formula, it is the simplest or most reduced. Chemical formula, which shows only the relative number of moles. So we are going to convert mass into moles. So as I said in one of the first lessons, we are going to use the mass over molar mass formula so many times that hopefully by the time you get to a test or the exam, you actually have that memorized. You don't need the formula. And so when you do empirical formula, many, many, many times, the empirical formula the calculations will show that it is the most reduced. So when we did ionic versus covalent, when you do ionic, you have to reduce the coefficients. And we talked about, say, I like MgO. So when you crisscross MgO, or crisscross Mg and O, then your grade 10 teacher maybe let you get away with this, but because it's ionic, of course, we reduced it. In Unit 1, if I asked you to draw the Lewis structure for Mg and O, you would have drawn this. Showing that magnesium gives away 2 electrons, oxygen gains those 2 electrons, showing 1 atom of each. And now we'll look at, if you're given mass amounts and you convert it to moles, can we quantitatively also show it's going to be 1 Mg and 1 O? And the answer is yes. So when we do the procedure, I guess, to find the empirical formula, I'll show you a way that you can organize your information. There is actually plenty of ways to do this. So I'm going to follow or organize my information using a chart so that one row will be mass, underneath this, or the second row will be molar mass or molecular weight, and then you will divide to get the answer. If you are a triangle person, you can certainly still do that. Same thing with even showing your work. So when we use the chart, one of the advantages is that it's sort of built like this equation. Some of you will not need to show the work to calculate molar mass anymore. Some of you will want to show your work. So we're kind of getting to the spot where you get to decide how this is going to look. Okay, so when you have a question, sometimes there could be 3 elements. If it was a macromolecule covalent compound, there could be 4. And so one of the things that you can do, we are going to change mass, which you're given molar mass, molecular weight from the periodic table. As always, we're going to always convert mass into moles. This new part is the last row. But because there's so many gram amounts you have, then using a chart can be one of the strategies to organize your information. So all of the information from hydrogen, I'm going to put in its column. All of the information for carbon, I'm going to put in its column. All of the information for oxygen, I'm going to put in its column. The next lesson of chapter 6 is determining the formula of a hydrate. So one of the columns will be a compound. The other column will always be water. You're trying to figure out how many water molecules there are. So this is just a tool to organize information. And one of the things about these questions, we already calculated percent composition, sometimes with molar mass and sometimes with grams, then you could be given grams in the question, or you could be given percentages. And when you're given percentages, it's really, that's a really common way to give information, because most people understand 2.2% hydrogen, 26.7% carbon, and 71.1% oxygen. People will recognize 71.1%. That's a lot of oxygen compared to hydrogen and carbon. But it's just a percent's kind of it's almost like a useless number. We don't really use that in our calculations. We always have to change it into something else. Sometimes you have to change it and divide by 100 or whatever. So in order for us to use it as a mass amount, no matter what our mass was, 2.2% of, if I said 2.2% of whatever the gram sample was, you would divide by 100 and multiply. So what we can do is, if your brain needs that kind of sentence, we'll always assume 100 gram sample. Because if you have 100 grams and 2.2% of it is hydrogen, how many grams do you have? 2.2, okay? So really we're going to use this percentage in the chart as the gram amount. The next slide has a bigger chart, so we'll wait, okay? So then, no matter what our sample is, it would be 2.2% hydrogen. So using 100 grams is an easy way to figure this empirical formula out, because no matter what where we are in the world, no matter what kind of sample we have, whatever this compound looks like will always be 2.2% hydrogen to 26.7% carbon to 71.1% oxygen. So what we really care about when we're looking for the ratio, how do they compare to each other? Not to all the carbon in the world or all the oxygen in the world, how do they compare to each other? So the way that we figure that out in the most reduced way, when you get to the end, you're going to divide each mole amount, so this line, by the smallest mole amount. And when you do the empirical formula, because it is the most reduced, lots of times the mole amounts, there's a couple that are the same. Maybe one of them is quite big. Sometimes all three of them are different. It doesn't matter. You don't have to guess. We are going to calculate, okay? So really, this is the only new part today, and really the only new math we're doing is dividing. And when you divide, then if you forget and you do it upside down, if you put the smallest number on top and the bigger number on the bottom, you're going to get a 0 point decimal, some kind of decimal number. And that's not going to make sense. So then you're like, oh yeah, I have to put the bigger number on top. So this sort of follows kind of what we've been, you do all the time, that we want a whole number, right? Number greater than 1. But let's see how this works. Okay, so sometimes people are very, very, very particular and they want you to assume 100-gram sample. Usually I'm okay with just plugging in the numbers. So hydrogen is 2.2 grams. Carbon is 26.7. Okay, and then you have from the periodic table, we're going to write down what is the molar mass or atomic mass of 1 hydrogen. What's the atomic mass of 1 carbon and 1 oxygen? They are together in a compound in some ratio that we don't know yet. Okay, so again, using the chart, you're going to do this row divided by this row gives you this number. This row divided by this row gives you this number. This row divided by this row gives you this number. You can show only your answer. That's fine. If that bothers you and you want to write it out all separately, you can do that too. Like you could write it out. Okay, you can do this, or you can just write the answer in here. So when you calculate the moles, then most of the questions are similar to this. The hydrogen and carbon values, are they almost the same? Yes, they are. So probably they're going to give us the same mole ratio. And then oxygen, if you ignore the decimal places, what's happening compared to the hydrogen and oxygen? How does 4 compare to 2? Double, yes. Okay, so this is a very, very typical type of question. We're going to get 1, 1, 2. It is not going to be difficult to figure out what the mole ratio is. Okay, so when you do decide, so the mole ratio, again, over here, it talks about dividing by the smallest mole amount. So these two are very close, but this one is smaller, okay? So I'll show, because this is the new step, I'll show my work. One of the elements has to be a 1. Whichever one you have decided is the smallest, that should be the 1. So hydrogen, I'm going to write the 1s in, even though you don't have to. The number of hydrogens is 1. Whoops. Whoa. Most of the time, the questions are going to get you, the rounding will be very, very straightforward. So here, 1.02 is really, really close to 1. And 2.04 is really close to 2. Most of the time, you would just round as you would expect. Okay, and then a very small number of cases will fall into this category. And again, you will find resources that will just round no matter what, except for 0.5. But if you have something that is greater, the difference is greater than 0.05, what are we going to do? So most of the time it would be like this, or it could be a little bit lower. Say this case could be like 1.9998, and you're like, okay, that's obviously 2. But what happens if you have something that is a little bit less obvious what to do? Okay, so this is not a common case. This one is for sure sometimes. Actually, no. But this is legit. Most places would make you do this. If it's exactly in the middle, then, should we round up? Should we round down? We don't want to take any chances. So you multiply the subscripts by 2. The other ones are less common, but they can be there. So if you had 0.3 or a third, you multiply by 3. This is my favorite fraction. What's 0.25 as a fraction? 1/4? Yes, so you multiply by 4. And then these two are the other cases of repeating. So 0.67, you multiply by 3, 0.75, which is like 3/4, you multiply by 4. Okay, and this does not happen very often, okay, but it does happen. So let's do this example here, but we're going to do the same thing. Most of the time, we just go in order that you're given. So in this case, I went CHO instead of HCO. Just do, if you want, it doesn't really matter. You can write out the words, you can write the symbols, you can fully write it all out with the formula. You do not need to use a chart. But again, I like it because then I can organize the information. 52 goes under carbon. Its molecular weight is 12.01. What you'll find is the questions will be sort of what you would expect. So let's say you had, I think one of the homework questions is aluminum and oxygen. So aluminum and oxygen, when you crisscross, there's a 2 and a 3. That's a unique empirical formula. And so you kind of know ionic compounds have to follow the crisscross rule. You kind of know what your answer is going to be. And then when there's 2 and 3 like that weird, you're probably going to do something like this. But most of the time, it's going to be, it'll be obvious how to round. Students always say, how many decimal places should I keep? Sometimes I'll just say, well, you know what, in this kind of question, because eventually we're going to round, keep as many as you can. But again, when I mark this, I keep my calculator beside my paper because if you round differently, your answer can be quite different. And I don't want that to determine whether you're right or wrong. Okay, so 52.2 divided by 12.01, 4.346. 6.15 divided by 1.008, 6.101. 41.7 divided by 16 is 2.06. Okay, and if you need a little reminder of what we did, and again, you can do this. You can not use a chart at all. You can show the formula every time. But because we have 3 gram amounts, then 3 molecular weights, and 3 mole amounts, and you have to decide which one's the smallest, then using the chart is a way to organize your information. Okay, so if you get a unique question like this, what will happen is, so these two are similar and these two are similar. So then what will happen is sometimes, like our case here, we're going to see 2 of them look like this. So you would multiply by the same number. one's going to be a 0.3 and one's going to be a 0.67, or one would be a 0.25 and one would be a 0.75, or one of them would be just a 0.5. And normally what happens when you get to the point of rounding, then if it's 0.67, for some things 0.67, your brain's like, am I going to round this up? 0.67, that's really close to 0.5. Should I round down? And then there's that ambiguity, and we're trying to minimize that, okay? So this one is the smallest. Oh, actually, maybe you want to prove it to yourself first. This is going to be the 1. No, you do not. Okay, so even this one, you can just write down the ratio. That's fine if you feel good about it. So 4.346 divided by 2.606 is 1.67. 6.101 divided by 2.606 is 2.3. Okay, so then again, oh shoot, is 1.672? Well, that's not very close to 2. Should I round down? It's again in this, the area of rounding feels a little bit ambiguous, and then hopefully that's your reminder, oh yes, I can't just round. But again, these two go together. If you had 0.3, you would multiply by 3. We have a 0.3. If you have a 0.67, you would multiply by 3. A 0.6, they're both the same, okay? So it's similar to math. What you do to one, you have to do to them all. We even have to multiply the 1 by 3, okay? So let's highlight that. And in the end, what you're trying to do is make the numbers not ambiguous. We would like a whole number. Also, most reduced, okay? So then if it is most reduced and now all whole numbers, then you can feel pretty good about what you've done, okay? So I'm going to multiply this one by 3. This one by 3, this one by 3. So 1.67 times 3 is 5.01, and that feels much more like a good whole number. Ooh, I'm out of room. 2.3 times 3 is 6.9. Okay, that feels like 7. Good. And then 1 times 3 is 3. Can 5, 7, and 3 be reduced? Nope, they cannot. And what happens is when I show this example, students think they're going to do this every time. If there are 10 questions for homework, you will do this once, maybe twice, okay? This is not a very, very common thing that you have to, that you're unsure of the rounding. More often, it will be one that you can round normally. And what you will, so you'll see, it'll be like 1.9997 or 2.00003, and you're like, oh my goodness, so easy to round. And then you'll get something like this, and you'll be like, ooh, what do I do? And then that's your clue. Oh yes, I have to do this manipulation thing. No, only if it's the decimal points are far, far away from the whole number, but not super far. Like, what do we do? Is 0.67, is it 0.5? Do you go up? Do you go down? You don't know, right? So then we multiply to get a whole number. Well, should you go up if we're talking about atoms? No. Okay, so this is a good question too. And again, depending on the resource you look at, some people will be like, come on, can't we just round? And some people will say, yes, you can. But if you are interested in thinking about the AP exam, I want to make sure you know how to do this. And our textbook does this, okay? So if you're a textbook reader even, it will do this. But there is plenty of cases where people would just round, except 0.5. Never would we round that, okay? Excuse me. Okay, so sometimes too, what you want to be able to do is take a look at the empirical and connect it to the molecular formula. You could do a question looking at some formulas. Are they empirical? So when you do the actual number of atoms, we don't want to be guessing anymore. We don't want to be ambiguous. We want to be correct, right? We're trying to be more quantitative. So doing the manipulation when the rounding isn't so obvious is the best way to do that, okay? So another type of question is something like this. If you are checking if something is an empirical formula, it has to be reduced fully. And sometimes it's super obvious. If they are both 6, is that reduced? No. Is CH4 reduced? It is, so it is an empirical formula. And then when you get into more complicated molecules that often appear everywhere in our bodies, C5H10O5. Does anybody know what this is? So it's ribose. It's in the sugar in our RNA. Is it the most reduced? No. So you would divide by 5. And the numbers are not going to completely become 1s like the first one. However, now this would be the most reduced. What about this one? C6H12O6. What's this? Glucose. And so you can divide by 6. No, you don't. Nope. So when you have these two sugars, which are not the same, in fact, glucose, if you take grade 12 biology, you'll talk a lot about metabolic processes. Everything we ingest in order for our brain to have energy has to be cleaved and changed into glucose. That's the only molecule that can cross the blood-brain barrier to provide energy in a metabolic process. So, but their empirical formula is the same. So then what is the difference? Why are they different? The structure is different. One of them looks more like a pentagon. One of them is more like a hexagon. And those kinds of physical properties affect receptors and how it can work. So when you do these, this is a covalent compound, all nonmetals. Then when you have that kind of compound, maybe empirical formula is not what we want. Ionic should be reduced. It should be the same, but we need something else. We need to be able to figure out what a molecule actually looks like. So how do we do that? That's right, molecular formula. So the molecular formula is the actual number of atoms in a compound. Oh, I don't know why this extra A is here. Yeah. So certainly when you have covalent compounds for sure that don't have to be reduced, then the compound could have the same empirical formula, but it would not have the same actual number of atoms, and it's going to influence its properties. Ribose and glucose are not the same sugar. So we need a way to actually figure out how many atoms are in the formula. This is a case where if a student, number one, when we do quantitative things, people will say, do you give us the formulas? There is not a good way to write a formula for this. It's kind of procedural, so it's definitely something that after Tuesday's quiz, you want to practice, okay? So, but the good news is when you do this kind of question, it's not ambiguous of what should happen, like what type of question it is. You have to be given what the actual molecular weight or molar mass of the compound is. You have to know kind of the answer-ish, and then we are going to figure out what number we should multiply by to get to the molecular formula. So we just went the other way. We knew what the molecular formula was. So C6H6, we could divide by 6 to get the empirical formula. These type of questions we're going to do, this is the molecular or empirical formula. What do we multiply by to get the molecular? That's what we're going to figure out. And, oh, it does say that here. It has to be a whole number. So when you do these questions, again, you should be like, okay, this makes sense. If I have the molecular weight is 120 grams per mole, then the empirical formula should be related to 120. So the empirical formula's molecular weight maybe is 60. And then you're like, okay, 120 divided by 60 is 2. You should be able to see the pattern, okay? So I'll try to write it mathematically, but some of you, if you're like, oh yeah, say 120 and 60, 60 times 2 is 120, you can show sort of a different amount of work here, depending on how your math brain works. Okay, so in this case, we are given the empirical formula, C, and I didn't write the ones this time, 1 carbon, 2 hydrogens, 1 oxygen. The actual molecular weight is 150. So there it is. We have to be given the actual molecular weight and the empirical formula. And when you do a question, whether it's percent composition, mass to moles, sometimes when you read a question and you're like, okay, this question only gives me one number, what can I do? I need some more numbers. Then, you know what? Use the periodic table and find the molecular weight. That's a great strategy. So here, if you find the molecular weight of this, we're not going to get 150, but we are going to get a number related to 150. So 30 is clearly lighter than 150. Is 30 related to 150 somehow by some whole number? What'd you get? 4.99995. So what would that be? 5. Okay. So some people will want to round now. So this is 30.0. So there's that extra decimal place for rounding. So you could do 150 divided by 30 and get 5 right on. Or if you leave the decimal places, even 150 divided by 30.026 gives you 4.99567. The ambiguity of rounding there is non-existent. That clearly could be rounded to 5. So either way will work. Ooh, I cannot spell. This is how my brain works. I can see that 30 and 150 are related. I would like to know how much bigger 150 is than 30, so I divide. You could go the other way. You could do 30 times 1, 30. 30 times 2, 60. 30 times 3, 90. 30 times 4, 120. 30 times 5, 150. There we go. I have to multiply by 5. So if you've done this correctly, you shouldn't get very far before you have figured it out, okay? But so either way, you can do the multiply way, which is more like trial and error. You can do this way where you divide. And again, if you did it upside down, you would get 0.2, you would get a 0 point number, and then you're like, shoot, that's not big enough. I didn't divide. I didn't put the bigger number at the top of my division statement. There's all kinds of ways to think about and check your answer. Please don't do all this thinking and then stop here. Remember, we want to find what is the molecular formula. Okay, so if our molecule needs to be heavier, how much heavier does it need to be? It needs to be 5 times heavier. So we're going to, and again, you don't have to show this multiplication step, but what you do to one subscript, you have to do to them all, okay? So students will say, Ms. Todd, how much work do I have to show? Do I need an answer statement? Is this okay? Whatever. When you're done, take a look at your question and pretend like you're marking it. And if you're like, oh, the answer's over here, no big deal, she'll find it. Maybe I won't. I showed someone their test in last period, and I took a mark off because he wrote his answer like in a crazy spot. He's like, Ms. Todd, there it is. And I'm like, how was I supposed to know that? So make sure that you take a look. I'm an old lady. Can this old lady give me as many marks as possible? And if the answer is no, maybe take a second, even if you put a box around it, okay? That draws my attention to your answer. Okay, so just thinking about the wording of the question. So sometimes you'll find that the question will talk about empirical formula, and sometimes the question will talk about molecular formula. And then you're like, wait a minute, why isn't it saying empirical? Why is it saying molecular? And so they're using the terms correctly, but being very specific. So empirical and molecular formula could be the same, which is true of many ionic compounds because they're supposed to follow the crisscross rule. But doing empirical formula, the chart method, is a way to quantitatively figure out what the polyatomic ion should be. So let's say this would have been a Unit 2 question. Write the formula for sodium sulfate. Sodium is 1, sulfate is 2 negative. How do you know that sulfate is 2 negative? What did I tell you to do? Oh, look at the back of the periodic table, memorize it. Did I tell you where that came from? No, I didn't. So now, if you were given the quantitative data, it would say a sample is whatever percent sodium, whatever percent sulfur, whatever percent oxygen, and you should get 2 sodiums, 1 sulfur, and 4 oxygen as your answer. So it's kind of a way to prove basically what we just told you to memorize before. Next year, we'll do Lewis structures for polyatomic ions. You'll see how chemically they're able or molecularly they're able to form. So now a question could talk about the chemical formula, empirical formula, molecular formula, because if you take a look at this, is it the most reduced? 2, 1, 4. Yep, that's the most reduced. But is it also the number of actual atoms? Yes, it is. So it is the same. Okay, so sometimes the wording, it's like tomato, tomato. It doesn't really matter. It is the most reduced. And it is the actual number. So when we do the formula of a hydrate, sometimes the question will say calculate or determine the formula of the hydrate. Sometimes it'll say determine the molecular formula of the hydrate. And it really is the same thing. Whereas a question like glucose, C6H12O6, which is a covalent compound, not ionic, no following the crisscross rule, then this is not an empirical formula. We already proved that. It's not reduced. But it's a better indicator of what glucose looks like because it's the actual number of atoms.